Howdy, hi, AP Calculus AB, and welcome back to another day of Topic 6, Applications of Integration and Differential Equations. This is actually the last part of Topic 6's application of integration. You hopefully have noticed that the last few days have been spent on themed free response style questions, right? We started with particle motion, we went to finding extrema. Last class we focused on tabular data, and this class we're going to focus on what are known as rate in, rate out problems. Once we finish this, so next class, day 86, we're going to jump into differential equations, which is kind of a sharp turn from what we're doing right now, but I think each piece of this topic 6 separately is too short, so we smush them all together. So let's get to it. Every year there's pretty much every year, at least recently, a free response on the AP exam features a problem with two different rates. Of course, when we think rates, we should also probably be thinking derivatives, right? Because everything on this AP exam is going to be in terms of derivatives, integrals, or limits. If you think of that in the context of particle motion, this is like velocity, right? Or velocities if there are two of them. Now, these two rates always complement each other. The first rate is going to describe how fast a quantity is accumulating, right? And if something is accumulating, you're gaining an amount of that stuff. And this accumulating quantity, or this accumulating rate rather, is generally known as a rate in. While the second rate is going to describe how fast a quantity is depleting or going away, or rate out. So two different equations, both of these are derivatives, and then if we put these two rates together, if we put together both how fast something is going in and also take into account how fast that thing is going out, we now have overall how fast the amount that quantity is changing, or how fast the amount of the quantity is changing. Where if our overall rate is positive, it means the quantity is increasing. However, a negative rate means the quantity is decreasing. Now you might be thinking, well, wait, how are there two different rates that are happening at the same time? How can something be both added to and taken away from something simultaneously? Well, I have one example for you here, and this example actually comes way back from the year 2000, probably predates when most, if not all of you are listening to this video were born, and I liked it enough that I actually changed it to match, or changed it, added on to make sure that there's more parts so we can cover every type of common rate in, rate out question that we see, right? A normal free response question only has parts usually A through D. This one has many more parts. And this is actually the only problem we're going to work through today, and it is a no calculator question. However, even though it's no calculator, I am going to show you various calculator tricks on here, and the reason I'm going to do that is because many of these problems are calculator active. I feel like the AP writers really enjoy making these calculator active because they can make the numbers as gross as they want. And so we're going to have to view this both from a calculator perspective and a no calculator perspective. So let's get to it. Water is pumped into an underground tank at a constant rate of 8 gallons per minute. See this gallons per minute? That's a giveaway that it's a rate or a derivative. However, this tank has a fault. Water is leaking out of the tank at the rate of the square root of t plus 1 gallons per minute. We have a second rate as well for 0 to 120 minutes, so 2 hours. At a time of 0, when we first start observing it, the tank contains 30 gallons of water. All right. Well, the very first thing on any one of these rate in, rate out questions, and you'd identify a rate in, rate out, right, because we have water being pumped in and water leaking out, is actually not a question, right? Normally a question would start with A is down here, but I always ask my students to do three things at the beginning. I ask them to identify their rate in equation, their rate out equation, and almost always there is an initial condition given. So what does this look like? Well, I'm also going to label these equations too. So let's start with our rate in equation. Which equation controls how fast water is being added in? Well, that is, of course, our first sentence. All right. Our independent variable is T every single time. And because the water is being pumped in, I'm going to say P of T is going to be my rate in equation. Now, P of T, notice I said that T is the independent variable. It's what we plug in, but they give us a constant rate of 8. Could we still phrase this as an equation? Sure. P of T is 8. For any time value you input, the water is being pumped in at 8 gallons per minute. At 20 minutes, how fast is the water being pumped in? 8 gallons per minute. And I am going to put the gallons per minute at the end. All right, what about that rate out? Well, they say water's leaking out, so I'm going to use L. The leak out at some time is given by, they actually gave us an equation here, T plus 1. That's also in gallons per minute. And then last but not least, what's the initial condition? Our initial condition is given to us at the end. At T equals 0, the tank contains, and so when I see contains, notice this is in gallons, not gallons per minute. That's an amount. So when I see an amount, I like to use A, and you can think of A stand for amount or accumulation, whatever sounds good. I'm going to say A of 0 equals 30 gallons, not gallons per minute, gallons here. These are derivatives. This would be an initial equation. So I always start with those three for any sort of rate in, rate out problem. There's no reason not to. You're going to have to use those over and over, so we should probably have them. All right, let's get to it. Part A. How many gallons of water leak out of the tank from 0 to 3? Well, if we're doing leak out, does it matter how much goes in? I don't think so. These two rates are independent from each other. So this leaking is just telling us how much is leaking out, and it doesn't matter how much is in there because the leaking out is just based on time. So this currently has units of gallons per minute. They want to know how many gallons. Well, we know if we took a derivative, L prime would be gallons per minute per minute. It adds on to the denominator, which means the antiderivative should destroy the denominator and just give us gallons. And we could see that like this. We're going to find the integral from 0 to 3 of L of t dt. And the quick way to check here, L of t has units of gallons per minute, right? And t, or the change in t, is still the change in time, has units of minutes. When we multiply those cancel and we're left with gallons. This is the right track. So what do we need to do? Well, we need to actually do the antiderivative of t plus 1 to the 1/2, right? dt. Okay, let's do this one by hand. Antiderivative, we need to add 1 to the power. And then we need to have something in front to offset the power. We're going from 0 to 3. Okay. As we move through, I would probably factor out the 2/3 and rewrite the 3/2 power as the square root of t plus 1 cubed. The cubed can go on the inside or the outside, whatever is easiest for you. Okay, and then we start evaluating. 2/3. We substitute in 3. 3 plus 1 is 4. Square root of 4 is 2, and 2 cubed is 8. Minus, now we substitute in 0. 0 plus 1 is 1. 1 cubed is 1. Square root of 1 is 1. And so I'm looking at 14/3 gallons. Watch those units. So from a time t equals 0 to t equals 3, 14/3 gallons have leaked out. Now someone might say, well wait, do we have to put a negative on there? No, they just want to know how many gallons, so that's a set number, it's a positive number, that many gallons. Now could you do this on your calculator? Certainly, you could type this into your calculator, hit enter, and you'd be fine. This is a no calculator problem though. I will show you a couple calculator tricks as we go through. Alright, so let's jump down to part B. How many gallons of water are pumped into the tank? Well, we can do this, no problem. Right, this is our pumped in. So 0 to 3, P of t dt. Checking, yes, that'll give us gallons, so we need the antiderivative of 8 dt. Okay, So we end up with 8t from 0 to 3, and this gives us 24 minus 0, which is 24 gallons. Now someone might say, well wait, you did a whole antiderivative thing. Couldn't I have just said that this is 8 gallons per minute? It's a constant rate and we're just doing this for 3 minutes, so couldn't I have just done 3 times 8? Sure, there's nothing wrong with that. You are generally expected to use calculus to solve a problem. Sometimes though there are ways to get around that. And full disclosure, I probably made this problem up. It goes way down to E, F, G. They probably wouldn't have done one of these original ones, so either way, they probably wouldn't have asked something that simple, but it is possible. All right. Part C. How many gallons are in the tank at a time equals 3 minutes? Well, this one is a little bit trickier, right? And the reason that this one is trickier is because we want to know exactly at 3 minutes how many gallons are in there. And I think there are 3 pieces of information that contribute to the number of gallons in a tank at any specific amount of time. First, we need to know how many gallons have been pumped into the tank over the first 3 minutes, right? If we find the total over the first 3 minutes, we'll have found how much is put in. Second, we'll need to find how many gallons have been taken out. But then lastly, we also need to know how many gallons were there to begin with. And so, when we set this up, I'm going to call this my accumulation function. How many total gallons have accumulated into the tank? And the way we do it is we take those 3 pieces into account. So I'm going to call this, we'll do it in black here, A of t, the total amount or the amount that's accumulated after a certain amount of time. Well, let's start with how much was in there at the beginning. The initial amount was certainly 30 gallons. Right? This is the initial. Okay? Then we need to add on the amount that is pumped in, right? That should make sense, shouldn't it? How much is pumped in there? Well, how do we find the amount that's pumped in? Well, some people will say, couldn't we just use this 8 right here? And the answer is almost, except 8 is not in terms of gallons, and my amount needs to be in terms of gallons. So how do we turn gallons per minute to gallons? Well, we use an integral, right? We need to integrate, I'll do this in blue, from 0, because that's where we know the initial amount, to when? Well, this is, oh, and that's funny. I guess I probably should have switched D and C, but that's okay. We'll get back to it in just a second. Well, let's just do it this way. So let's say that this is A of 3. So we're trying to find the total amount after 3 minutes. Well, we started with 30. We need to pump in from 0 to 3 of 8 dt. And then, and this is where things get tricky, we need to find how much has also been taken out from 0 to 3. And so the integral that we saw before was the integral from 0 to 3 of the square root of t plus 1 dt. But because this is being removed, we aren't going to keep this positive. We do actually need to remember to subtract the rate out. So we have our rate in, and then down below we have our rate out. This setup is very common. You take the initial, you add it to the rate in, and you subtract the rate out with integrals. The nice part is we already know these amounts. It is 30. We added in 24 gallons from 0 to 3 minutes, and then we subtracted off 14/3 gallons. Could you put this in your calculator? Absolutely. Do I want to do it right now? No, not particularly. So add it together, subtract whatever sounds good to you, and you'll come up with your answer. Okay, now this is very closely related to Part D. Part D says write an expression for A of t, and that's what I started to do on C before I realized how I'd set this up. For A of t, the total number of gallons of water in the tank. Well, we already found A of 3, the amount after 3 minutes. Let's find the amount after t minutes. The initial, I think, still has to stay the same. We still have to measure from 0 to something. This still has to be 8, and we still have to subtract the square root of things like so. Now there is a slight issue, we really don't want this t to match what's, for example, in here. Because when I replace this with 3 up above, did I replace the t with 3? And no, I certainly didn't. So this is where the concept, and we've seen this before, the concept of dummy variables come into play. I only want the 3 to get substituted into the tops of these integrals. That's the only place that we put a 3. So I want this variable up here to be t, because whenever we replace this guy with 3 or whatever number, the rest of those get replaced. And to make sure nothing else is confused in the integrals, we're going to just pick a different variable. Most commonly, x is used. So I'm just going to say this is x plus 1 dx. And so that way when I substitute 3 in here, I don't also replace that with 3 because now they're a different variable. And same thing over here. Instead of saying it's dt, let's just call it dx. So we keep all these variables the same, and you keep all these the same. All right. Why is a of t known as an accumulation function? Well, you start with 30, and then you accumulate more based on this rate, and then you lose some amount based on that, right? This is our accumulation function, or sometimes I think of it as the amount function, right? Nothing too bad. Okay, let's go ahead and skip on to the next page. Our next page over here, right, asks us to find an expression for a prime of t. Okay? A prime of t is, of course, going to be based off of a of t. Not too much of a shocker. So you might want to rewrite that a of t if it helps you out. Okay, and I'll do the same thing, I think. So we had, and I'll leave a little space here, we had a of t equals the integral from, oh, sorry, I forgot the beginning, 30 plus the integral from 0 to t of 8 dx minus the integral from 0 to t of the square root of x plus 1 dx. And if we want an expression for a prime, we need to take the derivative. And notice, because the input is t, we are going to be doing d dt of each side. The left side isn't bad, that's just a prime. The derivative of a constant is always 0, right? Because we're measuring the rate of change, and a constant can't change. Over here, we need to remember that the derivative of an integral essentially cancels out. This is our fundamental theorem part 2. But if you have a variable anywhere on your limits of integration, that variable needs to be substituted in to the variable in the equation. But 8 doesn't have a variable. 8 is just 8. Minus, and then when we take this last derivative, it's the same idea. This t needs to get substituted into the variable, and it looks like that. Technically, you should be multiplying by the derivative of what you plug in, which is 1. However, since it's just 1, why bother? And so we find a final a prime of t as 8 minus the square root of t plus 1. But haven't we seen those two equations before? Right? 8 and t plus 1? Oh yeah, they are our rate in and rate out equations. And so maybe it makes sense to you that the derivative of our accumulation function is explaining how the amount of water in the tank changes. And the rates that affect how the water changes are the rate that the water is going in minus the rate that is going out. And if you combine those rates together, it will give you an overall rate. And in fact, we're going to explore that in F. F says, is the water of the tank increasing or decreasing at t equals 48? What about t equals 80? And how do you know? All right, well, we can go through and do this right now. So increasing, decreasing, water is in gallons. Increasing, decreasing is like the derivative of what we're trying to find, right? That's how we do increasing, decreasing, which means if water gallons is a of t, then increasing or decreasing will be a prime of t. So I think this could be as easy as just finding a of 48. Okay, or I'm sorry, A prime of 48. I just said A prime. And so I'm just going to use our equation over here. A prime of 48 is 8 minus the square root of 48 plus 1. As we continue through, square root of 49, 8 minus 7 is 1. Let's give that some units. 8 was in gallons per minute. T plus 1 was in gallons per minute, so they have the same units. So when you put this together, then the units don't change, and we get 1 gallon per minute. All right, well, what does that mean? Is the water in the tank increasing or decreasing? Well, I see two ways to interpret this. Way number one is you can say because the derivative, because A prime is positive, then that means our original equation A is increasing. If A is increasing, that means the water in the tank is going up, right? The amount is increasing. The other way that I actually really like to look at this is I like to compare the rate in and the rate out. Yeah, so I like to kind of forget this A prime thing, and I'm like, okay, let's just compare and remember our, I forgot what colors I used, sorry. Remember that our pump in, the rate in, P of T was equal to 8. So what if I found P of 48? That would be 8 as well, 8 gallons per minute. Okay, then what if I compared that to the amount that's leaking out, right? This was the square root of T plus 1. So if I find L of 48, this is the square root of 48 plus 1, square root of 49, which is 7. Just compare those two rates. If we're pumping in at 8 gallons per minute and we're leaking out at 7 gallons per minute, is the overall amount going up or going down? And logically, I find my students go, oh, well, duh, it has to be going up because you're gaining more than you are losing. And sure, that would be a great way to explain it. So two ways to think about this. Don't forget to answer the question because they asked if the water's increasing or decreasing. The answer is increasing at 48. And you could either say because A prime of 48 is positive, or you could compare the individual rates and you could say something like because P of 48 is greater than L of 48. And by the way, even though these names weren't in the problem, by writing them, by giving them names on my paper, and you can do this on your paper too, even if these boxes aren't here, you could do it up at the very top of the problem. By giving them names, you can use those names all the way through the problem, right? So since I defined them, I'm allowed to say something like this, and they could be able to figure out what my equations are. All right, let's compare it. T equals 80. Okay, so same thing here. A prime of 80 equals 8 minus the square root of 80 plus 1. 8 minus the square root of 81, that's 8 minus 9, which is negative 1. Okay, same idea here. Because A prime is negative, the overall water in the tank is decreasing. You could also compare 8 and 9. 9 is our leaving or our leaking amount. We're leaking at a greater rate than we are entering, and so we are decreasing. When is the water level in the tank not changing? Well, for the water level to be not changing, I can think of two ways to do that, but I think relating this most closely to F, increasing or decreasing was all about A prime, and not changing, wouldn't that mean when the rate out and the rate in are equal, right? Let's say that you're going in at 8 gallons per minute, but you're also losing 8 gallons per minute, so you're filling up as much as you're losing. Yeah? So I think two ways to think about this. The first is you could say we want to determine when the rate of the overall water level is 0. A positive rate would mean the water level going up. A negative rate would mean going down. And of course that means we need our A prime of t equation, which was 8 minus the square root of t plus 1 equal to 0. But wait, there's more. If you add t plus 1, the square root of t plus 1 to the right side, we get this. The question becomes, when is the rate in equal to the rate out? Because if the rate in and rate out are the same, we just talked about this, then the overall amount is not changing because you're losing as much as you're adding. So there's a few ways to do this. You can realize the derivative must be 0 because the water level is not changing. You could also just straight set the two rates equal to each other. Either of those works, and then it's just a matter of solving, right? We square both sides, and we solve and end up at a time of 63. How do we know? We just justified with our work. Last but not least, part E. At what time is the amount of water in the tank a maximum? All right, well, they gave us a big time interval. They want to know the maximum amount. Oh, but hey, isn't that just like an absolute maximum? We want to know absolutely the largest amount. Now, they did ask for what time t. Okay, so there's a couple ways we can approach this, and I'll give you both ways right now. The first way we can approach this is we can say, well, this to me seems like the candidates test. We can say t, and we can say the amount after a certain amount of time t. Then we can go, okay, well, we also know that for the candidates test, we use both of the endpoints. We'll need to find those amounts. And then we also need to find any sort of critical points. Critical points occur when the derivative is set equal to 0. And that's nice. We found that earlier. That's 63. And then from here, you're like, okay, now I need to find 3 amounts. One amount will be 30. They told us at 0, there's 30 gallons in the tank. But then you have 2 more amounts to find. And so you would do the math by doing this guy up here, right? You have to do this 2 more times. And although that is okay, and it will absolutely get you the answer, we should notice that they just want to know at what time t. They don't actually want the overall amount. Now, if they said, what is the largest amount of water in the tank? Then yeah, you would have to do this candidates test. There's no other way around it, or there might be, but it's a little clunky. But if they're just looking for a time, I oftentimes find that a sign chart is the fastest. And so here's how I do my sign chart, right? I'd say, okay, I just always like to use the box as my reinforcement here. We're going from 0 to 120. There's 1 critical point. We already found all of this. We know between 0 and 63, 48 is a value there, and I tried 48 in the derivative, right? We're trying to look at the signs of the derivative, and that was positive. We also checked 80, and 80 was negative. And so I've had to do no math so far on this. If you look at my sign chart, this tells us that A of t will increase and then decrease. So based on my sign chart, is there a way to tell what time the amount of water will be a maximum? Well, visually, yeah, 63 has to be the largest, right? I don't know which one's the smallest, either 0 or 120, but the largest is very obvious here. And this is a pretty common little trick on these rate in, rate outs where you can kind of just get by with a sign chart and a justification as well. Here's what the justification looks like. We need to start by explaining how we know 63 is a relative max, because graders aren't allowed to look at this sign chart. The relative max that we've been doing for months, it looks like this, right? T equals 63 is a relative max because A prime of t changes from positive to negative. Cool. Now, how do we convince them, though, that that relative max is the absolute max? Well, we've mentioned this once or twice before. This is called the lonely critical point theorem, which isn't really a theorem. It's kind of more just a little affectionate thing that a lot of the teachers will use. So if there is only one critical point, and that is the point that you're interested in, then we can do this one last sentence, and we can say, as t equals 63 is the only critical point. And sometimes it's the only critical point on this interval, so it's probably not a bad idea to say it's the only critical point on 0 less than or equal to t less than or equal to 120. Then t equals 63 is the time when the water is at a maximum. Really, you could have just said, is the absolute maximum, right? If there's only one critical point, and that critical point is a relative max, then it's also an absolute max. If there's only one critical point, and that critical point is a relative min, then that is also the absolute min. And so this is essentially the lonely critical point theorem, where you first start by explaining it's a relative max, and then do the absolute. Could you have done it this way? For sure, especially if it was calculator active, then definitely do it that way, right? However, it can be time consuming to do a whole bunch of antiderivatives up there, so I like the sign chart method. All right, just about done for today. Some concluding notes though. First, lately these rate in, rate out problems have been calculator active. They've usually been the first or second problem, right? Those are the two calculator active problems, and they have some pretty gross functions. Let's take a sneak peek at the next page, right? This next page has two things to notice. First, you do need to state your rate in, your rate out, and your accumulation function. You could do just your initial condition. You'll have to do the accumulation function later. Then solve each problem. For full points, you only need to choose and solve two total problems, right? We have 1, 2, 3, and 4. You only need to choose two of those. Pick your favorite two, whatever ones look the easiest to you, and do those. But you'll notice that these functions are pretty wild. It's kind of tough to create functions that match real-world scenarios, and so they really have to stretch here, right? You'll notice that these are calculator active because I would not want to do math by hand with either of these functions. We should also notice, though, that there's a lot to these functions, and so they've named them E of t, L of t. In this case, E of t, and they usually have reasoning behind the name, are the number of people which enter an amusement park, and L of t is the number of people that leave an amusement park. And because they've named them, when you are showing work on your paper, you always need to show a setup and an answer, right? And our setup, you have two options. You could either write the integral from whatever a and b are, e of t dt, or you could write the integral of the entire equation. Which one takes less time? Oh, right, this one. So make sure that when you're showing work, you do have to show a setup, right? If they say, you know, how many people have entered the park? Don't just put like 4,000 people. You need to show where that came from. Integral from like 0 to 10. I'm just making up these numbers. E of t dt equals this. But don't use the whole function name. If they call it E of t, just use E of t. It's way faster. All right. Second, many problems will have you find where one rate is equal to the other, or where the overall rate is not changing. And so that's like what we saw up above, right? When is the water level not changing? That's setting a prime of t equal to 0, or it's determining where the two rates are equal to each other, right? So, if you set these two rates equal to each other, here is E of t, here's L of t, this will tell us in the amusement park problem on the next page, right, amusement park, this is when the number of people in the park is staying constant. The same number of people are entering as they are leaving. But the problem is you would have to solve this equation, which seems terrible. I would not want to solve that equation by hand. It's huge numbers, lots of factoring or quadratic formula. So instead, just use your graphing calculator to find the intersection. But the intersection of what? Well, we would need to graph two equations, one equation and the second. And so actually I'm going to take a quick second and do that because it's easier said than done on here. So I have this 15,600, and I'm going to need, I probably should have set this up ahead of time, apologies, but you guys should try this too. So while you're messing around with all this, then hopefully I'm going to be doing the same thing. So it was a fraction with 15,600. Oh my gosh, it's a rough one there. Second try. 15,600. I don't know why I'm doing it this way. Let's just attach my keyboard. That way I can flip back and forth way faster. Divided by that same polynomial, right? And then we're going to do the same thing for the other one. So maybe if you want, while I'm doing this, you guys can set this up. I'll show this on the 84 as well, just so we have both ideas here. So 15,600, t squared, 24t, 160. So x squared, 24x plus 160. Did I get those right? I did. And that's f of x. So then I'm going to do a second one. Okay, my second one, 9890. 9890 divided by x squared minus 38 plus 370. And notice I'm using x, not t. Okay, have those two graphed. Very exciting. What do we do now? Well, if we're going to find their intersection, right, I just graphed each side separately. And if I want to find where each of them intersect, we need to actually see those graphs. So is there a cheat way to see them? Yeah, kind of, right? In particular, we know that there's a 9 and a 23 in here. So my x-axis is going to go from 9 to 23. So I'm going to do Menu, Window Zoom, Window Settings. We're going to go from 9 to 23. No reason to look outside of that. I still don't see the graph though, which means we probably have to go up higher. How high up? Well, just try substituting 9 into each of these, E of t and L of t, right? However, they said at a time of 9 there's no people in the park. Probably doesn't help us too much. Let's try E of 9 and L of 9, right? So E was in F1 of 9 and F2 of 9 was the other one. And we're going to approximate this one. There we go. So look at these y values, 624 and 90. So I think then it looks like my y values have to be in the 624 range, but let's see what happens at the end at 23. So let's find E of 23 and L of 23. Should probably just get in the habit of doing the approximately, and L of 3, nope, 23. I'll remember it this time. We're going to do the approximately. Here we go. Love it, 395. So it looks like if I go up to the biggest one is 624, so let's go up to maybe 700. So we're in our graphing screen. We're going to go to Menu, Window Zoom, Window Settings, and we're going to go up from, 0 to 700. Ha! I've got my graphs. I'm so excited. Okay, so looking at this, I only see one intersection point. We can kind of approximate the shape. Maybe I should have gone higher than 700, but it seems fine. So I'm going to find that intersection point, right? Menu, Analyze Graph, Intersection. We need a few more decimals, though. Now, we have this number right here. Exciting. At a time of 15.7948 whatever, the two rates are equal. Hip, hip, huzzah. The problem, though, is if they ask you to do a candidates test after that, and you found the critical point, just like we did here, but it's a weird gross decimal, you do need to use the exact value, or as an exact of a value as you can find, and it needs to be more accurate than just 3 decimal places. So we do need to store this number and be able to recall it later. And so to store this number, just run your finger lightly over the trackpad over here until you can move your mouse freely. Hover your mouse over this guy until you see the hand, and then click once. Now, if you do it wrong or you click too many times, you can always hit escape and then try again. So you're going to click once. Okay. Once you've clicked once, then you'll notice that store, STO in blue over here, is accessed by doing Control and then store. And if you do that, it'll say, okay, cool, we need a variable to name this decimal over here. And call your variable whatever you want. A, B, Grant. You can use a name if you want. I'm just going to use A because I'm boring. Great. Now, did this just store it as 15.79481? Notice if I hover, it says it's linked as well. Let's try. So if I go back to my other screen and I type in A and hit enter, it looks like it just pulled a couple decimals, but if I go up and hit enter, oh look, it actually stored a very, very, very accurate value. It'll be accurate enough that you will not lose any accuracy in further calculations. And so if you were asked to do an integral, right, you would need to do that integral. Let's say I wanted to go from 0 to A or something like that. Instead of typing 15.794, you'd need to use that stored value within your integral. So be very careful there. Use that stored value instead of an approximation for the intersection. I promised I would show you how to do it on the 84 as well. If you guys are already done though and you're feeling comfortable, then you can stop this video and you can move on to trying 2 of these problems. They're all past AP questions. They are 1, 2, 3, 4, all calculator active as well. So good luck with that. 84, 83, Superstar, stick around and I'll show you how to store values on there. All right, so the first thing I'll need to do is probably type back in those equations. So I'm going to go back to my graphing screen really quickly, and I'm going to grab a list of all of those. And we're going to do, I guess they're both on this screen, so I guess we'll just do it that way. We'll exit this, and we'll do it right here. Okay. Clear all that. Get rid of that guy, and then we'll use the fraction shortcut on here. Nice. So we have 15,600. I said 600. There we go. Divided by x squared minus 24x plus 160. And there's the first guy. And then same thing for the second. 9890 divided by x squared minus 38. Oh, I think that put a negative. Interesting. I was trying the keyboard, but that to me looks like a negative, so let's try minus. There we go. 38x plus 370. Cool. And then we saw before, so I'm going to change that window on here. I think we went from like, I don't know, it was like 9 to 23 or something. And then we said, let's go from negative 10, sure, let's go to 800. I went to 700 last time. It didn't seem quite large enough. Window range, I'm going to hit quit. What did I do wrong with my window? Oh, I tried to go to 32 and I only typed 3. Thanks. But it should have actually been 23. That's what I was trying to do. There we go. All right, so there is my rate in, there's my rate out, and we want to find the intersection, so second, calc, intersect. When it says first curve, second curve, that's if you have more than one curve on here. Right now, so let's say that you had like 5 different graphs on here, and you wanted to find the intersection of 2 of those. Well, it tells you the graph you're on right now, y1, is this guy. Is that one of the curves where you want to find the intersection? Yeah, and then you also want to bring your little cursor, this little spider guy, as close to the intersection as possible, right? If I wanted to switch graphs, we just do up and down, right? If I do up, it switches me between y1 and y2. So the first curve, the first graph I want involved in this intersection calculation is this one. Hit enter and it says, okay, cool. Now, what other graph do you want involved? Well, there's only one other one here, but if it was the wrong one, you'd hit the up arrow till you got to the right one, move your cute little spider over to the intersection, enter a second time, and it says, should we guess between these 2 curves what the intersection point is? Yes, please. And we get that same 15.794, whatever. Now, this one is a little different than the Inspire. On the Inspire, you had to actually highlight this point and store it. On the 84, this value right here is automatically stored for you. Where is it stored? Well, it's telling you it's stored as x, the same way the y is stored as y. So if I quit and go back to the home screen and type in x right here, it's going to be that same intersection point, which is pretty cool. Except as soon as you do another calculation, it's going to erase that stored value. It's a temporary value. To keep that value, to use it later on, we need to store this as something else. So I always check it first to make sure it's stored, and then I just click the store button, because what's going to happen is if you don't type anything, it's going to reuse this answer. So I'm going to do store, and it says, okay, let's take this answer and store it as what? Well, now we need another letter, and I'm just going to use A again. It's pretty common. So alpha to access all the green letters, alpha A, enter. Now this is stored as A, and so anytime I type A in here, it will give you that value, and it will not change the value if you do extra calculations. So hopefully you got a bit out of this video. We were able to go through, work a rate in, rate out problem, and then you guys are going to practice all of this. I think really this is all the basics of rate in, rate out. The more you practice, the better you get. And I'm excited to have you back next class so we can start our differential equations.